Chemistry is the science dealing with the structure and properties of substances, the transformations they undergo, and the energy that is absorbed or released during these transformations. Chemistry deals with the building blocks of our world and explains how they are put together, how they fall apart, and how energy is produced or consumed in the process. We study chemistry, for example, to find out how water is formed out of hydrogen and oxygen, and why metal rusts in the winter.
The intro video from Carnegie Mellon's Open Learning Institute gives a great overview of Chapter 3, which is all about matter and energy. Chemistry is the study of matter and energy. This chapter lays some groundwork for us on terms that we will use and helps us get the big idea that atoms comprise everything. Oh, here's a picture of a room, and in this room we're saying everything we see and even everything we can't see, like the air, is made up of atoms. This is a graphite golf club, and here's graphite, which is just carbon, packed carbon. Here's a water bottle, and inside that bottle we have H2O. We want to start thinking in terms of atoms in this class. We're saying there are about 100 kinds of atoms, and the periodic table organizes them for us. On the periodic table, one thing you might see looking from one to another is that the bottom row might be different, and that's because these are all man-made elements. Chemists and physicists spend time smashing atoms together and trying to make new elements, but we'll say basically there are about 100 different kinds of atoms that comprise everything. So the formal definition of matter is that it's anything that occupies space and has mass, that is, these atoms. Some matter can be easily seen: steel, water, wood, plastic. That's because there are lots and lots of atoms and molecules, which is a term we haven't yet defined, clumped together to a substantial enough size that our eye can detect it. But other types of matter, such as air or microscopic dust, these are too small for our eyes to see. Sometimes a microscope will show them to us. When we use the word molecule, we mean that atoms have been joined together with bonds. Okay, that's the term, bond. Bonds hold these atoms together. So here is rubbing alcohol. We see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 atoms bonded together. The red one is supposed to represent the oxygen, the black ones represent carbons, and all the gray ones represent hydrogens, and they form bonds with each other and make a molecule. Are we able to see atoms with a microscope? We cannot see atoms. They are a billionth of a meter in size. But the scanning tunneling microscope has only recently been able to see atoms. And this is a picture from IBM of nickel atoms. Can we see molecules? Molecules can get really large. This is an image of DNA. DNA is a really long chain, and you know, hopefully, that it has a helical structure to it. It's a double helix, and you can almost make out that double helix pattern in this image. Well, a chromosome is about 1/millionth of a meter long, and that's getting in the range of the size of a human hair diameter. So we could almost see molecules, large molecules. Let's talk about the 3 states of matter. You're most familiar with solid, liquid, gas. That's because on our planet, our temperature and pressure conditions are amenable to having these 3 states of matter present. We say that solids are dense and packed tight. Liquids are a little more loose and flowing, and gases are spread apart and not dense at all. What I'm describing to you is the kinetic molecular theory. I call it the KMT. It's a really important theory that helps us understand things from a molecular perspective. So let's break this out a little bit. What we're talking about right now are the physical states of matter. It's all the same material. It's in different energy levels, which differentiates if it's a solid, a liquid, or a gas. There are actually 5 states of matter. I'm only going to talk about the Bose-Einstein condensate and the plasma forms rarely. We have an energy continuum. This is low energy, and this is high energy. also have entropy, which is disorder. So what we're saying is this is very orderly, and this is high disorder on this end. When we say it's very orderly, we mean strong bonds. And over here, it would be no bonds. There's no order at all to the way things are arranged. This is basically the big picture of the KMT. The 5 states of matter, Bose-Einstein condensate, is right around absolute zero, which is 0 Kelvin. All the way up through the plasma, which is an energized gas. Okay? Plasmas would be found on the sun and the stars, and on your plasma TV, and in your fluorescent lights. It's where you take a gas and you charge it. So on a fluorescent light bulb, for instance, electricity is put on the 2 ends, and it energizes the gas and turns it into charged particles. I want to now talk about the transitions from one phase to another, and I'm really focusing on solid, liquid, and gas, which are the 3 phases we'll work with this year. When we go from solid to a liquid, we have a term for that, and that transition is called melting, right? And we have a liquid and we go to a solid, we're really watching all of these bonds form, and that's called freezing. We watch the liquid become orderly with bonds. When we go from a liquid to a gas, what do we call this? Right, we call it boiling. And when we go from a gas and liquefy it, we call that condensing. So you should know all these transition names. In addition, we have one that's maybe not as common in our experience, which is sublimation, which is where we go from the solid to the gas directly. We're going to do a lab sublimation, and you'll like that. It makes it more memorable to you. When we have a gas and it goes directly to a solid without passing through the liquid stage, that's called deposition, or it deposits. Okay? So you should know the 3 primary phases of matter, and you should know these transition names. All right, let's go through solid and liquid and gas and their characteristics according to the kinetic molecular theory. So we say that there are strong bonds in the solid phase. We say they can vibrate only. Do you see this little vibration in this window? They kind of are shifting a little bit. It's very orderly. There's soldiers all lined up with bonds going in between them. This is a picture of sodium chloride, and we're saying that we have the little sodium atoms and the bigger chlorine atoms all in a 3 dimensions tightly held together. Packed so tight, they're very dense. We're so accustomed to solids not giving way under our hand, they are dense. There are really formally bonded solids called crystalline solids, and we will make beautiful crystals this year. There are also solids such as wax or glass that are amorphous solids, which is not as structured in the pattern. All right, let's look at liquids in our little picture into the molecular world here in the red. You can see the liquids have more movement. That's because they are making and breaking bonds constantly. They're spread out a little more than solids. However, we still say that liquids are dense. They're still very tightly held together, and therefore liquids are not compressible. This is the nature of hydraulics. You can push down on liquids and they don't give way. They assume the shape of their container. All right, let's look at gases. What are the characteristics of gases? They are wild and crazy, and they travel at high speeds. There are no bonds between gas molecules. They bounce off of each other like billiard balls. They're spread far apart, therefore they are not dense, and therefore they can be compressed. We see gases as compressible. They have so much space in between them. This bottom piston here can push on this gas and pack them tighter. a solid up above would not compress in this way. We're now going to go into a way to kind of organize matter into elements, compounds, and mixtures. This is a vocabulary exercise, but it's also a way that chemists order the world. We have a flow chart. We're going to work through this systematically, going from left to right. Okay, in all of matter, things could be pure or they could be mixtures. That's our first branching. A pure substance is composed of only one type of atom or molecule. We're going to define mixtures as composed of two or more different types of atoms or molecules. Let's look at the elements. The elements are from the periodic table. We say there are about 100 of these. They cannot be broken down into simpler substances. Here we have little copper wires, and they would be pure copper atoms lined up. Here you have a balloon filled with helium atoms. They're pure. It's just an element. Let's look at compounds. The word compound means we have several atoms joined together with bonds. Here we have sugar cubes. These are the sugar molecules. It is pure. They're all sugar molecules. Here's water. It's pure water. It's only H2O present in that liquid. Compounds are more common than pure elements because elements tend to be reactive and they combine with other elements to form compounds. Now let's look at the far right side of mixtures. Mixtures is when two or more different atoms or compounds are mixed together. Air is an example of a mixture. Air has oxygen and nitrogen. Or seawater is a mixture because it's not just the water, but it's the salt too. Mixtures can be either homogeneous or heterogeneous. Homogeneous means that it's consistent throughout, such as sweet tea. The sugar is dissolved in the water and it's spread evenly throughout. Heterogeneous is like an oil-water combination where the oil sits on top of the water and we can clearly see the separation in the phases. Let's go through and wrap this up by filling in the blanks. What do you think would be the appropriate way to finish this statement? Matter may be a pure or it may be a Let's use the word, one word we could use would be a substance, meaning it can be an element or a compound, or it may be a mixture. It could be pure or it could be a mixture. A pure substance could be either an blank or a blank. What can be pure? It can be a pure element or it can be a pure compound, such as pure water. A mixture may be either blank or blank. Well, we can have either homogeneous or heterogeneous mixtures. Heterogeneous is where you can see the different materials that are mixed together. Mixtures can be composed of two or more blank, or a combination of both. Well, I think what we're looking for here, elements or compounds. We want to just gain mastery of these terms because we'll be using them throughout the year. That's it for sections 3.1 through 3.4. When we get into 3.5, we're going to be dealing with how do we separate mixtures and how do we tell when we're rearranging atoms.